Welcome back, everyone, to another explainer. Today we're diving into and demystifying the complex kinematics of neutron moderators. We're going to break down the incredible physical journey of a single neutron inside a nuclear reactor, and we'll be relying entirely on the foundational physics and engineering equations that make controlled chain reactions actually possible. So if you've ever wondered how we tame subatomic chaos, you are absolutely in the right place.
So picture this as the ultimate subatomic pinball problem. When a fission event occurs, a neutron is ejected at terrifyingly high speeds. We're talking about an energy level of 2 mega-electron volts, 2 MeV. So the real question is, how on earth do we slow down such a wildly fast, highly energetic particle without just losing it completely?
To put that into perspective, look at the sheer scale of the energy drop we need here. A neutron has to drop from 2 million electron volts down to a mere 0.025 electron volts. That's a microscopic fraction of its original speed. If we don't bleed off that kinetic energy, the neutron won't be successfully absorbed by other fuel nuclei to sustain the reaction. The reactor literally relies on this extreme deceleration to stay alive.
Okay, let's take a quick look at our roadmap for this neutron's journey. We'll cover the physics of the crash, how we measure that energy loss, choosing the perfect moderator, comparing slowing down density versus flux, and finally, the escape probability.
All right, starting right off with Section 1, the physics of the crash.
The core mechanism for hitting the brakes on a neutron is called elastic scattering. Think of this like a cosmic, high-stakes game of billiards. You've got your moving neutron acting as the cue ball, and it just slams right into a stationary target nucleus inside the moderating material. Now, because it's an elastic collision, the total kinetic energy of the system is perfectly conserved. But, and this is the crucial part, a chunk of that energy is transferred from our neutron to the target, which slows the neutron down.
Now, looking at the actual kinematics of this energy loss, it can look a bit dense, but it's basically this. E1 is the neutron's initial energy before the crash, and E2 is its energy right after. The math shows us that depending on the exact angle of the strike, there's a specific maximum and minimum value for E2.
These extremes are actually super clear when you break them down. If it's just a glancing collision, the neutron barely clips the target, right? So it keeps almost all of its energy. Here, E2 basically equals E1. But if we get a direct, head-on collision, that is where maximum energy transfer happens. The absolute minimum energy the neutron can drop to is determined by the Greek letter alpha. So E2 minimum equals alpha times E1. Essentially, alpha acts as the mathematical floor for how much speed a neutron can lose in one single, perfect crash.
Moving right along to Section 2, measuring energy loss.
So, how exactly do we calculate the rate of this energy drain as the neutron pings around? Well, in an elastic collision, on average, the neutron's energy drops by a constant factor, and that's completely regardless of its initial energy. The ratio of E1 to E2 stays constant. Basically, the neutron is shedding a steady percentage of its speed with every single crash, rather than losing a flat linear amount.
Now, tracking an exponentially decreasing energy level gets really messy really fast. So physicists use this brilliantly counterintuitive concept called lethargy, which is represented by the letter U. Lethargy is calculated as the natural log of a reference high energy divided by the current energy. What does that actually mean for us? It means that as the neutron's actual physical energy drops through all these collisions, its lethargy value increases. It's just a really clever mathematical trick to track the whole slowing down process on a much simpler, linear scale.
Okay, Section 3, choosing the perfect moderator. When we look at different nuclides based on their slowing down parameters, it's wild how much they differ. Remember, we're trying to get our neutron from 2 MeV down to that crucial 0.025 eV. To do that, hydrogen only needs 18 collisions. Deuterium takes 25. Carbon, that requires 115. But we also have to factor in the moderating ratio. And look at deuterium. It is staggeringly high at 12,000 compared to hydrogen's 72.
Looking at the real extremes here, hydrogen acts as fantastic brakes. Since its mass is pretty much identical to a neutron, it can drain the maximum amount of energy in a head-on collision, needing just those 18 bumps to reach thermal speeds. But compare that to the massive, heavy nucleus of uranium-238. That requires a staggering 2,200 collisions.
But here's the catch. Just being good brakes isn't quite enough. An ideal moderator definitely needs high scattering power, absolutely, but it also desperately needs a high moderating ratio. It has to bounce the neutrons around efficiently without accidentally absorbing them. A poor moderator might be great at slowing neutrons down, but if it has a high absorption cross-section, it just eats the neutrons. It literally destroys the chain reaction before it can even continue.
That brings us to Section 4, slowing down density versus flux.
All right, let me challenge you with a quick question here. When you have billions of neutrons crashing around inside a reactor, what exactly is the difference between the slowing down density and the neutron flux? Let's build these definitions using the core equations. We've got QE representing the slowing down density and phi E representing the flux. By definition, QE is the number of neutrons per unit volume per second that pass through a specific energy level, E. On the flip side, the flux, phi E, is tied to the collision density. It relates to the total path neutrons take as they occupy those lower energies in the moderator.
Actually, a really great way to separate these two concepts in your mind is with a traffic analogy. Slowing down density, Q, is like standing on a highway overpass and counting the number of cars passing a specific mile marker in 1 minute. It's all about crossing a specific threshold. Neutron flux, on the other hand, is like calculating the total combined mileage driven by all of those cars within a certain section of the highway. One measures passing a specific point, and the other measures the total interaction space.
And finally, Section 5, the escape probability.
Ultimately, it all boils down to this deceptively simple mathematical fraction, QE divided by Q0. As our physics outline explains, Q0 is the initial strength of the neutrons, basically our starting population. QE is the number of neutrons that actually survive all the losses and absorption to successfully pass through our target energy level. So, this fraction represents the ultimate survival rate. It's the escape probability of our bouncing neutron population.
And I just want to remind you why this absolutely matters. Out of the vast initial burst of neutrons produced in that very first flash of fission, only a very specific fraction are going to survive the gauntlet of the moderator to reach those 0.025 eV thermal energies. The entire efficiency, the safety, the basic operational reality of a nuclear reactor depends entirely on calculating and controlling this exact survival rate.
Which leaves us with this final thought. We've seen the extreme mathematics of the crash, the lethargy of energy loss, and that crucial survival fraction. But if slowing down neutrons without absorbing them is the master key to unlocking sustainable reactor power, how do engineers go about perfectly balancing that ultimate moderating material with the fissile field itself? It is a delicate, incredibly high-stakes balancing act of physics. Hopefully this explainer has given you the foundational lens to understand exactly how it works. Until next time, keep learning.